It's my pleasure to introduce Professor Francis Arnold, the Linus Pauling Professor of Chemical Engineering, Bioengineering, and Biochemistry at Caltech. And I see that she mentions that her research focuses on protein engineering by directed evolution. Well, I'm not sure that I understand, but I hope that within the next 45 minutes I'll know more about it. But I want to mention that Professor Arnold is involved not only in basic science, but she has also established two companies. And when I asked her, how are they doing, she told me they're doing fine. So I wish her success both in her basic science and in her industrial companies that she has started. Professor Arnold.
I'm delighted to be here and thrilled to be in Israel for the first time. It was 1987 when I was a brand new assistant professor at Caltech that I attended my first enzyme engineering meeting. And at that meeting, Ephraim Kachalski-Katsir was winning the Enzyme Engineering Award. I'm sure that wasn't his most important award, but it was a wonderful opportunity for me. I spent several hours talking with him about the problem of engineering enzymes, because the world had been using enzymes for all sorts of practical applications, but had to develop processes to compensate for their frailties. My idea was that I would go in and modify the sequence of a protein to give it the properties that would make it more suitable for processes. And I was also thrilled with the idea that a president of a country would be an enzyme engineer. And I liked the idea of a country that would have an enzyme engineer as its president. So I thought that was marvelous. So that's what I am. I'm an enzyme engineer. I wanted to build new proteins because I was born in the era when we could start thinking about manipulating DNA. I was a graduate student in Berkeley at the beginning of the DNA revolution, when we could go in and manipulate the sequence of an organism or a protein and possibly even give it new properties. But as we've heard just now from George Whitesides, that dream was a little bit difficult to implement, because just as we cannot compute or design a ligand to bind to a particular protein, we also cannot design a particular sequence that is better than what nature gives us and solves a human problem. And this I was told when I was a grad student, so I see some young faces in the audience. And by the way, those at the Weizmann who were at my talk last week, I apologize. You can fiddle with your phones. You've been through this before. I was told when I was a graduate student that the protein folding problem would be solved in 5 years. As we say in English, pants on fire. That problem, how a polypeptide sequence encodes a folded protein, is, I suppose we're better off than we were 35 years ago, but not that much better off. It's still a major question. But the big question of how sequence encodes function has not been solved. You cannot sit down and design an enzyme from first principles, and especially an enzyme that solves a real problem, that functions better than what nature has provided, or better than your competition in chemistry. It just won't happen. And I'm disturbed to say that it hasn't happened in all of these years. Of course, I think Ari will object, but he gets it after I do. This is a fundamental challenge that has not been solved. Of course, my challenge was more practical, and that was to get tenure at Caltech quite a few years ago when I didn't have any clue of what I was doing in designing a new enzyme. So what has changed? What has really changed, of course, is that we have an amazing set of technologies. This technology of manipulating DNA, of recombinant DNA, is what inspired me, and what saved my life, though, was the ability to read and write DNA now, 30 years later, in ways that we couldn't even dream of back then. It was hard to do the experiments back then. Making a single mutation could take weeks. And then, of course, studying how that mutation affected function took additional weeks. And I realized I wasn't going to get anywhere useful by making one at a time. Today, it's so much easier. You can read DNA essentially for free. The advances in sequencing are enormous. You can synthesize any DNA you want. You just write out a sequence on your computer and email it to your favorite supplier in Northern California or in Israel, and you get back in by FedEx the actual DNA sequence. So we can read, we can edit DNA. You've heard all about CRISPR. So you can go in and manipulate DNA. What we cannot do, and this summarizes what George said and what I just told you, is we cannot compose DNA. We are writing with our baby scissors, cutting, and we are composing great music, we hope, but we don't know how to do that. And 4 billion years of evolution has given us quite a bit of beautiful music that we can hope to learn from, but we can't begin to write like that. So I will propose that composing is a grand challenge for chemistry and for biology. Understanding reverse engineering, that's called biochemistry, is a huge problem, but any kind of forward engineering of biological systems requires that we learn how to do this composition. So there I was 30 years ago trying to build better new proteins without understanding the principles, and we still don't understand the basic principles. But I realized that somebody did it, and it's called evolution. Evolution is a marvelous composer so that we can look at the sequences of proteins that exist today, that you can just scrape from the bottom of your shoe. And you can see from those sequences and the family trees that you can build, you can see that they came about by this simple, elegant algorithm. Algorithmic process, turn the crank of mutation and natural selection, such that the enzymes that exist today are all beautifully tuned for their biological functions, and they've been designed through this process, which gave me an idea. If I didn't know how to design a protein, maybe I could use evolutionary algorithms to do that. And the technology was just coming into play. The first 96-well plate reader was just beginning to be available in the early 1990s. Grab that, now you can do 96 experiments at once. Error-prone PCR was coming into play so that you could make mutations. Now let me point out first, though, that humans have been doing this for a long time. We've been modifying the biological world at the level of DNA. We have been composing new DNA by artificial selection, making everything from corn to carrier pigeons, lab rats, racehorses, you name it. We have been modifying these organisms to suit our needs, making corn that will feed the large populations that we have to feed, making creatures like this that are not remotely natural. Right? This is not something that you would find in the absence of humans to support it. It fulfills our needs, but if it got out into the natural world, it would be eaten, for sure, by the coyotes in my neighborhood in Los Angeles. But these serve our purposes, and we don't have to understand the sequence-function relationship in order to create these improved biological things. Now, in the past, of course, in natural evolution and in the farmer's barnyard, and in corn breeding and everything else, the mechanisms for manipulating DNA sequence, the underlying diversity of the DNA sequence, those mechanisms have been very conservative, very limited, such that worms go with worms, monkeys go with monkeys, but crossing them probably won't work very well. You wouldn't get a very useful biological object out of that if you could even do it. And you couldn't control the rate of mutations that go in unless you smoke a lot of cigarettes. Maybe you could have a few extra mutations, but it's pretty limited. Now remember though, this technology has changed. So if you want to become a forward breeder, a breeder of molecules instead of dogs and cats, you can make any DNA you want. So you can cross DNA from different species. You can have 3 parents. You can have 33 parents. You can dial in any level of mutations that you want to provide the underlying diversity on which artificial selection can act. And that's good news, right? You have total control over the evolutionary system. I decide who lives and who dies. I'm only working with proteins, so don't get too nervous about it. I decide which go on to acquire mutations in the next generation. So you can think of this really as a molecular optimization problem. It's a tough problem, right? Because think of all the ways that you can string together amino acids to make up a protein. It's bigger than the number of particles in the universe. It's bigger than the United States national debt. It's a really, really, really big number. Most of those are useless, but you could find some things that work. Otherwise, we wouldn't be here. So we can think of forward evolution as molecular breeding as this optimization problem that nature solved. And that tells us something about the fitness landscape on which a protein has to operate. So if it's very rugged, if this fitness, and the fitness is defined by me, the breeder, because I decide who goes on to the next generation, the fitness can be very rugged. If that landscape is rugged, then mutations will cause the protein to unfold or not function. But obviously, we wouldn't be here to talk about evolution unless the landscape looked a lot more smooth. If it's perfectly smooth, of course, we have this Fujiyama landscape in which any random uphill walk will take you to the global optimum. And life doesn't look like that either. But it was argued by people smarter than I, even in the absence of sequences to look at, that the fitness landscape must be smooth in some of its many dimensions. And this is a terrible picture. I apologize for it because I only have 2 dimensions to work with. But the dimensions are all the ways you can make a mutation to a protein. So there's thousands of dimensions. There's thousands of ways that you could mutate a protein and not destroy it. And what happens is that there are few ways that you can mutate a protein and walk uphill in a fitness landscape, especially when you're starting with something that's not very good, something that does not solve a human problem. So we argued that there must be some smooth paths in this fitness landscape. And what does that mean? That means that you can implement a very simple set of experiments. And this is how we did these experiments in the early 1990s. You can copy DNA that encodes an existing enzyme. You can control the rate at which mutations are made using error-prone PCR. And if you make mutations, you can easily make gazillions of genes with mutations in them. The cells, of course, do the hard part. Those translate the mutant genes into mutant enzymes. And then the hard part for the human being, the breeder, so to speak, of molecules, is deciding who is better. So you actually have to measure each one. This is the glory of microbiology. You plate all these bacteria out onto a plate, put them into 96-well plates, and then do good old-fashioned hard work, analytical chemistry, to measure which enzyme, for example, is more active than the one you started with. Now, of course, most mutations are deleterious. That's the hard part of this. And the other hard part is deciding how high to set the evolutionary bar so that the rare beneficial mutations can be reliably acquired. In other words, I have to set up a screen that is sufficiently sensitive to measure the effects of small numbers of mutations and do that in a background of thousands of things or hundreds of things that are not as good as what I started. So it's just doing good old-fashioned, careful analytical chemistry. But if you do that, this algorithmic process, you can iterate on it and climb up the fitness landscape reliably. And that's what's glorious. It really works, so that hundreds of laboratories now use this directed evolution process to overcome the fundamental ignorance of how sequence and codes function. And as a result, over 25 years now since these were first published, it's obvious that proteins will adapt, and they'll adapt quite rapidly to new challenges. And you can get big changes in their function with changing a small fraction of the sequence. This is what we didn't know when we started. How quickly could you get measurable, useful changes in enzyme function? Turns out it's pretty fast. Whereas in biochemistry, right, these are the products of often neutral drift, so that many mutations might be accumulated, hundreds of mutations, with only a very small adaptive component. My experiments give only the adaptive component. Now here's the scary fact for the would-be designers of enzymes. We often identify mutations that are 20, 30 angstroms from an active site of an enzyme that confer measurable functional changes. And of course, we can't even explain those. We can't explain why they give those changes, much less predict them. So we still have a ways to go before design will be able to do the same thing. So to summarize 25 years worth of work, lots of people's labs, is that directed evolution is a great optimizer of enzyme function, and you'd be surprised at how many of the products in your daily lives you use that are actually made by directed evolution. Everything from the enzymes in your laundry detergent to many of the drugs are now being manufactured using enzyme processes, enzyme engineering, just as Kachalski-Katsir envisioned. This is now a reality in industry. And you heard I start companies because every once in a while we do invent useful catalysts. But I want to talk about a grand challenge and something that I have been working on for the last 5 years because it's so much fun. The grand challenge, of course, is to find ways that we can populate this earth and not destroy ourselves and every other species that we have to share it with. And that will require some pretty clever chemistry, chemistry that allows us to use renewable resources and not create pollution, and also things that are recyclable. So to do that sustainably, we have to be excellent chemists. And I would argue that the best chemist on the planet is, sorry, Nobel laureates and Wolf Prize winners, it is nature. The best chemist on the planet is the biological world. And if you could learn to program biological things like bacteria, we could envision making the fuels and materials that we need in our daily lives. Now, my colleagues at Caltech, they pat me on the head and they say, oh, that's so cute. You know, you all have been saying that for 20 years and it's just not happening. We're hearing a lot of 20-year stories that are just not happening because we're not very good at manipulating biology. And one reason is that biology makes what biology wants to make. And there are a lot of transformations invented by humans that are the basis of the current chemicals industry. So my friends at Caltech say, you know, biology is cute, but can't do what I can do. And that is true, because 100 years and more of creative synthetic chemistry has given rise to our synthetic world. We live in a synthetic world. Many of the products have bonds that don't even exist in nature. All right, so that's what I decided to work on for the last 5 years. How can you get biology to compete with my really brilliant colleagues at Caltech and elsewhere? And what does that mean? That means making enzymes that catalyze reactions not even known in nature, invented by human beings. And that's hard to envision if you think about it superficially, which I did for 20 years. How would you get an enzyme to catalyze a whole new chemical reaction using a conservative process, such as a random uphill walk accumulating a single mutation at a time? How do you build a whole new active site this way? And that kind of thinking kept me from taking on this grand challenge, or at least a little tiny piece of the challenge. But if you think a little further and talk to your biology friends, you realize that nature invents and innovates all the time. And here's just one story that has actually been answered at a molecular level. Atrazine, we have been dumping billions of pounds of this potent herbicide onto our planet for about 70 years. And it was first thought to be non-biodegradable. But then, poof, all of a sudden, some microbe figured out how to degrade, to dechlorinate atrazine, thereby giving itself a rich nitrogen source that gave it a selective advantage over its neighbors. And that organism populated the earth such that now atrazine is biodegradable. How did that happen? Well, it happened because an enzyme that had already existed, that was actually able to degrade melamine, had a little bit of activity on atrazine. It wasn't its biological function, but it had a capability as a side activity that then became the fuel, the starting point for evolution, such that random mutation and natural selection gave it more and more. So this is the picture I can leave with you of how nature innovates through this process, is that it's already there. The innovation is already there. And I like to say, to the graduate students, you are selected for being able to work 80 hours a week or maybe 100 hours a week at low pay, right? And that's what you do to do science. But you maybe can play the piano, or you could wash dishes or take a job in some other industry, given a new opportunity. And that's exactly what's going on. You have many capabilities. Well, so do enzymes. This vast collection of enzymes that exists on the planet has more capabilities than you can begin to imagine. And when those become relevant in a changing context, those get drawn out by this optimization. So how do you implement this in the laboratory? You can, provided you can recognize what these new capabilities are. So let me give you some examples. One way to recognize new capabilities is to go to the old biomimetic chemistry literature. Remember that in the 80s and 90s? It was the hot thing to think that you could build an enzyme mimic that didn't have all that spaghetti around it, that could do the same thing that an enzyme could do. Singularly unsuccessful, right? Those protein components are actually useful. But what did people do? They went on beyond where nature had gone and shown that sometimes these enzyme mimics could do other chemistry. So if you go back to the 80s and 90s literature, you can find examples like this in which an iron phenylporphyrin complex was used to cyclopropionate an alkene. Now, this is not a natural reaction, right? There's nothing natural about these components, and it's done in organic solvent. But this is what gave us a great idea. It's not remotely interesting until you ask whether a protein can do that. So you go back to the old literature, and then you pull it into a new protein and ask, well, golly, could instead of hydroxylating a CH bond, inserting oxygen into a CH bond, which is amazing chemistry done by a cytochrome P450, could it create a reactive carbene? And there was plenty of evidence to think that that was possible because carbene precursors are great destroyers of enzymes. But the interesting thing is to ask, can it make that reactive carbene and then transfer it to a second substrate inside of an active site that was built for some other purpose, maybe even just oxygen binding? Well, it turns out that if you start asking those new questions about natural systems, you can find some pleasant surprises. Turns out that heme, just free heme and water, will catalyze this reaction 70 times before it gets self-alkylated. Same sort of selectivity, making the trans isomers and no enantioselectivity as the TPP complex. Cytochrome C will do it. Myoglobin will do it. Even a P450 will do it. Here the protein is actually lowering the activity. 5 turnover numbers. Nobody would even report that, right? You couldn't get your paper published if you reported that. But that's the gold. Because I just told you, if a little bit of activity is there, it can be optimized through evolution. Now, we sometimes contaminate our beautiful blind experiments with thought. George, this is for you. Blind is beautiful, but thought is dangerous. In this case, thought told us that if we want to do this inside of a living cell, we would have to monkey with the machinery of a cytochrome P450 because it's beautifully tuned by nature to not be reduced in the absence of its favorite substrate. And I can tell you that styrene is not its favorite substrate. So we argued that if you changed the absolutely conserved cysteine ligand of this protein to a serine, maybe we could pump up the reduction potential and actually get this reaction, which requires reduction to the iron 2, to go inside of a cell using not dithionite, which we had to force it outside the cell, but using the endogenous reductant. And that works really beautifully. And in fact, if you do that, you get just the right change. And you get a sickly green protein. Now, if you work with cytochrome P450s, you see they're beautiful red. Well, it turns a sickly green. That had already been reported because people love to show that you could kill a P450 by changing out the cysteine with a serine. Well, let me tell you, that protein ain't dead. It is just waiting for you to ask what it does. So we call this a P411 because it's lost its lovely carbon monoxide binding peak at 450, but it's a P411. And just, I'm going to keep this suspense high. You can think of this as, for if there's anybody in the audience who does transition metal complex chemistry, this is a DNA-encoded, self-assembling chiral metal complex that I can just tune through evolution just by typing in that DNA sequence. So when you do that experiment, just typing in a new DNA sequence, you can build the cysteine variant of the protein, and you can manipulate the outside residues for selectivity, thereby creating inside of a living cell the best cyclopropanation catalyst, or very close to the best cyclopropanation catalyst that's ever been reported, using iron, not dirodium. So this was exciting. That's meant that we could make things like the difficult cis isomers and do it with very high EE, all for sugar. These bacteria will gladly do it if you just give them sugar. And that means that you can manipulate the same sorts of proteins in this similar way. And we demonstrated a couple years ago that you could make the chiral cyclopropane cores in a single step, the desired stereoisomer out of the 4 possibilities in a single step, no protection, no deprotection, all for the cost of sugar. So I want to share with you some of the fun new stuff, and we wanted to go beyond showing that we could do, let's see, George, as you said, that's the sausage making. All right, maybe that's sausage making, because chemists are pretty good at making cyclopropanes. We wanted to started doing things that synthetic chemists couldn't make. So we started looking at, this is a recently published paper, looking at highly strained cyclic compounds. And if you add a double bond to a cyclopropane, getting a cyclopropene, we're into 50, 60 kilocalories per mole. Make a bicyclobutane, we're at very high strain energies, and these things are extremely difficult to make. But we argued that perhaps this same carbene transfer chemistry could be used, and that holding it in the active site of a tunable enzyme would allow you to make a single stereoisomer of that. And in fact, Kai Chen, this was his idea, and so basic process is, as I was showing you, use a carbene precursor like EDA, not a natural compound. And these compounds are very rare in nature, and they've never even by any chemistry been shown to be made with an iron catalyst, yet these proteins will gladly do it if you train them enough. So Kai found a P450 with a little bit of activity and evolved it into different versions that will make different stereoisomers. So he could make stereodivergent versions, and then he could make versions that had the ability to take quite a range of substrates to make these cyclopropanes. As far as I know, nobody cares. This is always the thing. We make these molecules. Nobody really cares about these cyclopropenes yet, but now they're available, all for the price of sugar. So I'm hoping somebody will come to that. But let's go to bicyclobutanes. That one's an odd molecule and extremely difficult to make. No one's ever made these as pure stereoisomers. But it turns out an enzyme is perfectly happy to do it. And this is quite a challenging thing. No one could design a catalyst to do this. Let me just tell you that. These cyclopropenes are very reactive, and they have to be held in the active site of the enzyme to enable the second cyclopropanation to take place, thereby making the bicyclobutane product. I think there's one example in the literature of doing this with an osmium complex with no stereoselectivity whatsoever. But an iron complex inside the active site of the enzyme will do that, and you can do it at prep scale. We've made hundreds of milligrams of these things. Once again, I'm not sure anybody cares, but they do go pop when you pull on them, so they have a lot of energy, and they could be useful, for example, for rocket fuel binders or various applications. And they're all made in bacteria. Living cells will do this chemistry. Let me finish with a couple of stories that I particularly love. This is from a couple of years ago, but I wanted to go beyond where nature has ever gone, making bonds that don't even exist in biology. Cyclopropanes exist, cyclopropenes exist. They're made by different roots. Even you can find a bicyclobutane. They're all made by different roots. But you don't find any organosilicons. Biology has never put together silicon and carbon to make organosilicon compounds. All the biology uses silicates, so there's silicon-oxygen bonds, but there's no silicon-carbon bonds. But there's 50 products in this room that have silicon-carbon bonds in your hair and in your cosmetics and in the caulks and sealants. Humans invented this chemistry, and it's useful chemistry. So what would you do to get biology to make carbon-silicon bonds? Well, once again, you go to the literature and see what chemists have done. The transition metal catalyst literature for carbene insertion into SiH bonds is kind of short and sad. If you look at the metals, they're things like rhodium, iridium, very often these expensive metals that are not sustainable. And the turnover numbers, the biggest turnover number you can find is 97. So this is not really very useful chemistry. The enantioselectivities are good, I'll admit that. Notice there's no iron. No iron has been reported to do this. And we had to work hard to screen. I have refrigerators full of thousands of human proteins now, and we screened a few hundred of those. And we discovered that, in fact, there's a lovely cytochrome C from a halothermophilic organism that you find in Iceland in a salt pool, hot salt pool. Little tiny protein. Super stable. 106 degrees centigrade is its melting temperature, which means you can boil this protein. This means you can dry it and give it to your chemist and not even tell them it's a protein, right? This is a great little protein, and just the wild type version, the one that you can get from a database, will take dimethylphenylsilane and methyl EDA and form a new carbon-silicon bond with 40 turnovers and 97% EE. So it's already there. The innovation is already there. It's just never had a chance to tell you what it can do. Now, for the designers and the ones who think that looking at a computer model of this will tell you something, this is what the active site looks like. And Ed Solomon jumps up at one of my talks and says, that's impossible. You know, there's no free coordination site in a cytochrome C. And that's true. There's a methionine ligand on one axial ligand, there's a histidine underneath, and then heme occupies. Where's the chemistry happening? If you roll your little ball of solvent into the active site, you find a volume of 0. So how does this happen? Well, it turns out that nature doesn't care about your calculations. This is happening because proteins are dynamic. And this weak methionine is obviously coming off, and it allows this enzyme to catalyze this reaction. Not only does the enzyme, this is an electron transfer protein, which happens to have this as a side activity, but it's evolvable. And in just 3 generations of mutation and artificial selection, measuring who catalyzes the reaction better, you can make something, improve it by 40-fold, and already make something better, 15 times better than the best human-invented catalyst that I showed you. And it does it inside of living cells. And these catalysts, because of the nature of this active site, which is sitting as a little indentation on the surface, it accepts a wide range of substrates, and we made in this one paper 19 new organosilicon compounds. Once again, I don't think anybody cares. You know, I've made thousands of new molecules and nobody cares about. But these are there, and they're perfectly enantiopure. So if anybody is interested in these, this is a great way to make them. But I will point out, let me just point out, what's interesting about this is the chemoselectivity. Because I just told you that these proteins will cyclopropionate alkenes, or you can make bicyclobutanes from alkynes. But once you've evolved it to accept the silicon hydrogen bond, it doesn't touch those. So you can train the active site for perfect chemoselectivity as well, such that if you give a bacterium this substrate, normally if you have dirodium, you're going to insert into the NH bond, as well as the SiH bond. You get a statistical mixture of things, but with the protein, you just get one product. And the cells will give you a good yield and good selectivity, all for sugar. Now, I want to tell this story because there's new unpublished results which may please those who want to understand what's going on. It's going to be hard, but this little stable protein is easily crystallizable. The crystal structure was already reported, but then we were able to get the crystal structure of this triple mutant at very high resolution. And I'll just point out that it looks like its parent. It has 3 mutations from its parent, so its overall structure looks like its parent, but there's a big change in this loop over the so-called active site. And what's happened is that this loop has pulled out, all the residues in the loop have pulled out into the solvent. And what does that do? That creates an active site, a big active site. So even though the initial enzyme was competing with the methionine ligand to do the chemistry, now it has an aspartic acid at that position, and it will catalyze thousands of turnovers. I think maybe if you were looking at some of the numbers on the slide, the best we can get is in the tens of thousands of turnovers for this chemistry, and it's created an active site with these 3 mutations. Once again, I'll just say no one can predict how these mutations would give this kind of structural and functional change. What's even more exciting is the evolved enzyme creates this reactive carbene. So if you feed the methyl EDA to the enzyme crystals, it will actually, you can soak it in, and you can take a crystal structure picture now of the reactive iron porphyrin carbene. And this is the first time that such reactive intermediate has been actually observed at very high resolution inside of a protein. In fact, I have to brag and show this OMIT map for that, which illustrates all the tight interactions that it's making. These are all hydrophobic contacts, but it's making these really nicely designed interactions in the active site. And this configuration of the carbene fully explains the R selectivity that we observe. So we know how the substrate can fit in and explain, and now we're collaborating with various groups to do molecular dynamics simulations and DFT calculations in order to see if we can predict new reactivities. Let me finish up by saying I love sausage making because I have one algorithm. It's called evolution. You turn the crank and you get free novelty from it. So why stop with silicon, right? There's a lot more elements out there. And this is Southern California, Death Valley, near my home. And if you look at this stuff here, you see boron. Boron is another element that nature has not incorporated into organic compounds. This is Boron, California, which needs a new economic base, and perhaps I can provide that here. Los Angeles here, that star there, that's my little institute, the California Institute of Technology. There's a big space full of boron. Biggest boron mines in the world are in Southern California. But nature never figured out how to make carbon-boron bonds. Does she care? I can't really say, but she never had the opportunity. And now it's time to give her the opportunity, because now if you take water-soluble boranes that are stable in water, and these carbene precursors, we can make carbon-boron bonds now that are tunable, enantioselective. And this shows the evolutionary progression. These are now 400 times better than the best human catalyst. So not 15 times, 400 times. And we just stopped when we figured we could get the paper published. We haven't stopped because it's already optimized. Nature learns really, really fast. And if you use this crank, you can do some pretty interesting things, I think. So we've shown that you can use different diazo compounds, incorporating into these organoboranes, lots of functional groups that are useful. For example, these trifluoromethyl groups, and then these become useful synthetic intermediates for pharmaceutical chemistry. And it's all tunable by evolution. So what I've tried to show you is that nature has limited chemistry. It's amazing chemistry, but her toolbox is vast but limited. And the kinds of bonds that she can make, or at least that we've discovered, I'll tell you a quick story if I have time about things that are discovered after we publish them, but we know of only carbon X bonds that have hydrogen, nitrogen, oxygen, sulfur, and a few other things, a few halides in there. But basically, there's a whole lot of the periodic table where nature hasn't gone, but humans have gone. And now what I've shown you is that we've added 2 whole new elements to the periodic table of elements that nature can use. You can now form frameworks inside of living cells, and of course then that offers a lot of possibilities for biological modification and elaboration. So you could gang these enzymes up with natural modifying enzymes and now create whole new families of compounds, all by programming the DNA. So I'm not going to tell you, this is a third story, which I'm not going to tell you because my time is up, but if you can do this with carbines, you can also do it with reactive nitrines. So we've published maybe 5 or 6 papers on direct CH amination using enzymes and iron complexes instead of rare metals, where you can do aziridination, CH aminations, and a lot of really interesting carbon nitrogen chemistry. So with that, I'd like to summarize some ideas, and this is a grand challenge audience, so I want to look to the future here. We've just scratched the surface of what biology can make, right? And we're just starting to put together these tools of molecular biology and protein engineering with all this brilliant chemistry that's been invented over the last 100 years. So you've got this remarkable evolutionary algorithm, right? This evolution capability that circumvents your inability to design and compute. Doesn't matter. Because now if you know, if you've got some intuition of where functions can be found, you can improve that reliably through evolution. And thereby marry what you know about synthetic chemistry with what I know about protein engineering. And if you like the biochemistry, if you want the understanding, and there is some subset of my group that really does want that, including me on some days, we want to understand how these new functions came about, we can go in and look at the answer up front, get their structures, try to understand the mechanisms by which these changes came about. And with that, I'll thank a really brilliant group of young people who did all of the work that I'm talking about today. And thank you for your attention with this.